Hello, this is the walkthrough for the Physics Unit 2 exam. This one is the extra specimen paper that I've created using the ordinary specimen exam paper. It's just slightly different. It gives students an extra bit of practice. This exercise of observing the walkthrough is really a post-marking correction exercise, but also to teach students a little bit about exam technique and how to use the various physics techniques to answer questions from these papers. So you put your name at the front, you've got your formula sheet as per normal. Looking at it, what's going to be useful today, we know that the acceleration due to free fall is going to be important, and we know that the Suvat equations are going to be important, and that's about it. There isn't really much else that's of any intrinsic use. So let's start from the beginning. So we've got question 1. A pupil conducts a simple experiment to measure the acceleration of a ball rolling down a slope. They release the ball from a chosen distance from the end of the slope and time how long it takes to reach the end. They measure the distance using a tape measure and the time using a clockwork stopwatch. That's one you wind up. It's got a little spring inside it that keeps it going. So we've got a table of results. So we have to suggest the uncertainties. We don't know it for sure, but looking at the numbers that are written down here, the uncertainty of the stopwatch is going to be to the nearest 0.1 seconds. Okay, because that's the smallest change that they were recording. And likewise with the tape measure, it's 0.01 meters, the nearest centimeter. They've obviously been a little bit lazy with their measurements. You need to calculate the mean value of the time taken to reach the end. So that's 1.8 plus 2.1 plus 2.2 divided by 3, which is going to be 6.1 over 3, which comes out to be 1.03. You can leave it as 1.03, but really and truly as it's here, we should call that 1.0. However, that value is quite useful when you're doing your calculations later on. Calculating the percentage uncertainty of the pupil's measurement of the time taken to reach the end. So it's the uncertainty in their measurement of time. So it's the range of times divided by 2 gives you the uncertainty. So it's the range divided by 2. So the highest reading of time is 2.2. The lowest is 1.8. So the range is going to be 2.2 minus 1.8 over 2. Well, that's going to give me 0.2 seconds, but it wants the percentage uncertainty. So that would be the percentage uncertainty is the time, uncertainty in time divided by the time. So that's going to be 0.2 over the time measured, which is going to be, just realised I've made a very silly error there. It should be 2. I was reading off the wrong bit of my notes. So over t, which would be 2.0 more or less. So it would be 0.1, which means it's plus or minus about 10%. You can leave it as 0.1, but you shouldn't really call it 0.103 or anything like that, just simply because it doesn't really as a 101 or anything like that, simply because really percentage uncertainties are usually to the nearest percent. Moving on, the pupil uses the formula to calculate the acceleration of the ball. So it's at squared over 2d. The more astute of you will have worked out which of the Suvat equations that is. To calculate the acceleration, this is all about technique really, isn't it? So the acceleration is 2d over t squared. This is kind of a no-brainer, isn't it? So d is the distance, which is 2.1, and t is 2 seconds, 2.0. So that's going to be 2 times 2.1 over 2, which is going to be about 2.1 meters per second squared. Okay, and that's the correct units. We know that because it's acceleration, so it should be pretty simple. We know that if the value is above 9.8, then something's probably gone a little bit wrong. So, have I done that correctly? Have I done that correctly? It looks about right. Well, have I done that correctly? Should have noticed straight away that something is wrong. What have I done wrong? Well, it's a common mistake made by candidates. It's t squared, so that should be 2 squared. So that is clearly wrong. That's 2 times 2.1 over 2 squared, so that would be 1.02 meters per second squared. So that's where it goes wrong. Very common mistake, don't make it. The next one is to calculate the percentage and absolute uncertainty of the pupil's measured value of the acceleration of the ball. So we know the acceleration is 2d over t squared. So here we're dividing two values there, so we have to add together the percentage uncertainties, plus that's squared, so it's been divided twice, so it's twice the percentage uncertainty. So our percentage uncertainty in A is going to be equal to the percentage uncertainty in D plus twice the percentage uncertainty in T, because T is squared. So that would then mean that if we substituted that in, well, the delta T there is going to be 0.01, because that's the uncertainty in the measuring equipment. We didn't take repeats, so there's no range to divide by 2 or anything like that. And we reckon that D, according to our previous table, was 2.1 meters. So that's 2.1 plus 2 times, well, we know that's already 0.1015 or something like that. So I'll say 0.1. You can see that that one pales into complete and utter insignificance, really. But if you do add them together, it comes out to be 0.205, I think, 0.205. So nearest makes no difference. 21% uncertainty. That one is kind of disappears into insignificance, really. So then you've got your value there of 0.205. So we know that the actual uncertainty is going to be well, we made it 1.02, didn't we? So it's 1.02 multiplied by 0.21 is 0.214, so that would be 0.21 meters per second squared. Okay, so that gives you the absolute uncertainty. That's the percentage uncertainty. It is quite all right to say that the percentage uncertainty is 20%, because it rounds off quite nicely. So moving on, the student suggests replacing the clockwork stopwatch with a more precise digital stopwatch. Suggest whether this would improve the quality of the results and explain why. Well, a digital stopwatch, if you think about it, yes, it gives you an extra degree of precision in the actual reading, but it doesn't give you a degree of precision in terms of the actual measurement, because actually the biggest error caused, that features in this experiment is going to be the reaction time of the person doing the experiment. So suggest will this improve? Well, frankly, no. Well, you don't get any marks for that. The idea is that the random errors caused by reaction time are far greater than the precision of the stopwatch. Okay, so the actual reaction time is the source of the error. Even if you use a digital stopwatch, you'd still have that big range of results. So number 2, you've got this motorbike. Question 2 always involves some kind of automotive thing, so because it's always a motion question. So figure 1 point shows a picture of a motorcycle. That helps you to identify what a motorcycle looks like. Table 2 contains data about the motorcycle you will need to use throughout this question. So it says show the maximum acceleration of the motorcycle is 2 meters per second. Well, it's a 1 mark question, so they're not looking for mega physics. It's using F equals ma. So A equals F over m. Force is going to be 500 newtons because that's the force accelerating the motorcycle. That's the braking force there. It might come in later, I guess. So typical mass of the motorcycle, well, it doesn't talk about the mass of the rider, so we're going to assume that it's all together. That comes out to be 250 kilograms. So 500 divided by 250 is going to be 2.0 meters per second squared. No brainer, really. Then the motorcycle accelerates to top speed. Calculate the maximum possible time, the minimum possible time, sorry, to accelerate to this speed. We're assuming constant acceleration at the where the only force acting is the maximum accelerating force. So that's going to be using Subat equations. You could use a variety of different equations. I'm going to use V equals U plus AT because I'm given the value of A. So I want to work out the T. Well, we know that is equal to 0. We know that that is equal to 80. We know that is equal to 2. So we can work it out. So it's 0. So it's V minus 0. So it's still V divided by 2. So that's going to be 80 over 2, which will give me 40 seconds. Okay. How do I know it's that simple? It's a 1 mark question, so you know it's going to be a very, very simple method. You're not looking for anything complex. The next part of the question is to do with calculating the distance travelled while accelerating. So we're still playing with Subat equations. So let's just go off the camera a little bit there. There we are. So calculate the distance while it's travelled while accelerating. Well, you could use a variety of different things. Use V squared equals U squared plus 2AS. For sake of argument, I'm going to use S equals UT plus a half AT squared. I know it involves me using my value of time that I measured before in the previous question. So, but as long as I show my working, the error will always carry forward. So S equals a half AT squared because the initial velocity is 0. So we know that that is going to be half times the acceleration, which we said was 2, times by the time, which we said was 40 squared, gives you basically it's 40 squared, which is 1,600 meters. Okay, which for a vehicle getting up to top speed, it's going to take a mile or so to get up to top speed. In fact, the motorcycle travels twice this distance before reaching top speed. Calculate the actual average acceleration of the motorcycle. So the average acceleration, well, if we think about it, we're going to use very similar physics. It's Suvat, V squared equals U squared plus 2AS, where S is going to be 3,200 meters because it's twice that distance. It tells you there, twice this distance. So we want to work out A. We know V is the same, it's still 80. So if we want to work it out, we know that A, we rearrange this to make A equals V squared over 2S. Well, our V squared is going to be 80 squared divided by 2 times 3,200, which basically actually comes out to be 1.0 meters per second squared. It's half the acceleration, which kind of works. Right, the motorcycle has a top speed of 80 meters per second. It said so previously in the question. Don't know why it repeated itself, but there we go. So explain in terms of forces why the motorcycle has a top speed, and it's 2 marks. So basically they just want, first of all, what are the other forces here? Well, we know that we have air resistance and friction. And we know that the air resistance and friction forces increase with speed. Okay, so as the speed of the motorcycle goes up, the air resistance and all the friction forces are going to start increasing too. Okay, and that's until they are equal and opposite to the driving force or the accelerating force. Now that implies that the net force the total force, or the resultant force, is equal to 0, which implies no acceleration. Whoops, gone off the page a little bit there, never mind. But you get the idea. So the next one is to show the theoretical maximum power output from the motorcycle is 40 kilowatts. Well, you should know by now, power is equal to force times speed, times all velocity against in the direction of force. So that's going to be force, which is 500 newtons, multiplied by the top speed of 80 meters per second, comes out to be 4.0 times 10 to the power of 4 watts. Dead easy. Easiest 2 marks of your life. So then you have to estimate the distance the motorcycle could travel using 1 kilogram of fuel, stating the assumptions you've made. Well, the biggest one is, of course, the 1 kilogram of fuel contains a certain amount of energy, and we're going to have to assume that all of that energy is used to do work against friction. So we're going to assume 100% efficiency, which we know is not really true. But we're going to assume it because we've got no other data to go on. So if we're assuming 100% efficiency, then the energy from the fuel is going to be equal to the force times the distance. There are lots of other ways of doing it, but that's the simplest way to do it. And we know that force is 500 newtons, so we can work out the distance. Well, the distance is going to be the energy from the fuel divided by the force the motorcycle has to push. So if we work that out, if we get our data out again, the force is 500 newtons. Whoops, the force is 500 newtons. The energy for 1 kilogram of fuel is 4.5 times 10 to the power 7 joules per kilogram. So the energy for 1 kilogram of fuel is 4.5 times 10 to the minus 7 joules per kilogram, divided by a force of 500, gives you 90,000, or 9.0 times 10 to the power 4 meters, which is about 90 kilometers. So then it says, explain whether or not you regard your estimation, say your estimation, there's a typo there, your estimation to be a realistic value for the distance travelled using 1 kilogram of fuel. Well, 90 kilometers, it's a bit long for for just 1 litre of fuel. But 1 kilogram of petrol is just over 1 litre, so it's not really a good value for it. It's a little bit high. It's the right order of magnitude. Motorcycle usually does about 10 kilometers per litre of fuel, so it'd be about 10 kilometers per kilogram, but very high. Okay, so the value is very, very high, but it says explain it. Well, it's very high, so there'll be lots of energy wasted, by the engine, etc. A petrol engine is only something like about 30 to 35% efficient at best. So the last bit then says, the motorcycle stops using a maximum braking force and comes to rest from top speed. Calculate the distance travelled while braking. So we know from our data table the top speed is 80 meters per second. The force trying to brake it is 1,500 newtons. We know the mass of the motorcycle is 250 kilograms. So if F equals ma, A equals F over m, which is 1,500 over 250, which is 6 meters per second squared, is the deceleration. So if we think about it, Suvat, we want to know the distance. That's what we want to know. We know the initial velocity is 80. We know the final velocity is 0. Okay, because it comes to rest. We know the acceleration. We don't know the time. So we're using v squared equals u squared plus 2as. So we know that's going to be 0 equals u squared plus 2as. So u squared is minus 2as. So S is going to be u squared over 2a, it's going to be minus s. Now of course a is negative, so the u squared is the initial velocity, which is 80, so it's 80 squared over 2 times minus 6, which comes out to be minus 533. So that would imply about 530 meters or so. Okay, two significant figures will do nicely here. That's how you do that one. Next one is actually a momentum question, which I've cut down because I know some people hadn't done much on momentum yet. So what we've got here is got a bullet hitting a block, and it's a way of measuring the speed of a bullet. But we're just going to do the first half of this question, of the actual full question here that I've set. I've actually cut the second half off. So we want to state the combined mass of the block and the bullet. Well, this should be a no-brainer. If you've got the mass of the bullet is 0.01, the mass of the block is 1.99. How convenient. 2.00 kilograms. If you do not use the correct number of significant figures, you don't get the mark on that one. Calculate the gravitational potential energy gained by the block and the bullet. Well, you know it's the height's raised. That height is 22.1 centimeters, so that would be mgh, which is the mass, which is 2 times 9.81 multiplied. Now be careful, that should be 0.221. 0.221. Okay, and it comes out, I'm not going to play with the calculator here, I'm going to use my notes. It comes out to be 4.34 joules, which sounds about right. So then we're assuming that 100% of the gravitational potential energy of the block and the bullet came from its initial kinetic energy just after it was struck by the bullet. Show the initial speed of the block and the bullet just after the bullet struck the block was 2.1 meters per second. So we know the kinetic energy is a half mv squared. So v equals, well, v squared is going to be 2 times the energy over m. It's got to be square rooted. So that energy is actually that value up there. So that's the square root of 2 times 4.34 over the mass, which is 2.00, which comes out to be 2.08 meters per second, which is approximately 2.1 meters per second. Thereby it's shown. Okay, that's all you really had to do. Pretty easy. Now the next question involves filling in a table. So you've got 5 missing values. You're literally just doing a calculation, so you're literally just working out what that is squared. So 0.69 squared, for example, comes out to be 0.4761. Now if you put that in, you would not get the mark, because all of these are to 2 decimal places or 2 significant figures. So this should be 0.48. This one comes out to be, well, you're just doing the calculation every single time. So that's 0.56, 0.64, 0.72, 0.79. All you've got to do is square it and give it to 2 decimal places. Not exactly difficult, and that's a little bit of an unrealistic 3 marks. Normally you'd get 2 marks for something like that. So we're using the graph paper on the next page to draw a graph of horizontal distance squared versus the launch height h on the x-axis, because we've got this weird experiment here. I mean, these graph questions are so formulaic that actually half the time you can actually ignore the actual description of the experiment until later on. The only thing that's useful there is it's got an initial horizontal velocity of 4 meters per second. So he wants to put d squared on the y-axis and then h on the x-axis. So what we want to be doing here is fairly simple. We want to be just adjusting a scale. So the maximum value of h is 0.5 on our values. So we could go 0, 1.1, 2, 3, 4, 5. That'll do. It's nice and big scale. Okay, we use ink, we use rulers. Okay, you can use a pencil. You're more than welcome to use a pencil, but I do insist that you use a ruler. Now the maximum value for d squared, well, it starts off pretty close to 0 at 0.08. It goes up to 0.79, so it's about as near as makes a difference, 0.8. So if we look at this, we go from 0, 0.1, 2, 3, 4, 5, 6, 7, 8, just about fits, perfect fit. 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and that's going to be labelled. Remember, we always label our axes. It's h squared in meters squared, okay, because it's a distance squared. So all we then need to do, oh, sorry, it should be d squared, I do apologise, it should be d squared. So all we need to do is do that. There we are, d squared. All we need to do is just take it all the way up there like that. So it's a nice straight line. It doesn't have to be a work of art, but it has to be clear. We then plot our results. Well, our first one of d squared is 0.08, so that's up there, and that corresponds to a launch height of 0.5, so that's there. So we cross the 2 over, we put a cross. Now when you're doing data points, you can put a cross, or you can put a dot with a circle around it. You can put range bars in if there's a known uncertainty, but to be honest with you, it's surplus to requirements here. So we just plot our results. So literally, it's just very, very easy to plot your results. They go up by 0.05s along the x-axis. So we're just really going along 0.05. So 10 there, 0.10 is 0.16. At 1.5 it's 2.4. At 2.0 it's 3.2. At 2.5 it's 4.0. At 3.0 it's 4.8. At 3.5 it's 4.6. Sorry, 5.6 I should say. At 4.0 it's 6.4, so 6, 1, 2, 3, 4. 4.5 is 0.79, sorry, 0.72, so that's there, and 0.05 here, the last one, goes up to 7.9. Then you use your 30 centimeter ruler, which you should have, and you just draw a line of best fit. Now with these graphs, typically they follow a straight line graph pattern. Okay. There it goes. Okay, so it's a straight line through the origin, which is what we would expect. And then the next part of the question then asks you to calculate the gradient of the graph and give appropriate units. So the gradient, it's the same technique as always. The same technique as always. We pick two convenient points on the line. So I would avoid picking data points simply because it can be confusing. So I'm going to pick a point just here. And I'm going to pick a point somewhere up here. I think there's quite nice. Goes, it's, you can read it quite precisely. So then I just take my values, take my gradient measurement, and I draw a nice big triangle. It's important. The technique here is more important than the values you get. Which sounds a little odd, but it's true. Okay, because remember, I'm examining your technique, not examining whether or not you can get the right value for G out. So this one has a y1 equals 0.75. The lower value of y I'm going to call y2. It is equal to 0.11. My higher value of x is 0.47. And my lower value of x is 0.07. Okay, so what I've done is I've actually looked at my values for x and y. So then I want to actually put that onto my gradient calculation. So I know that my gradient is delta y over delta x, which is equal to y1 minus y2 equals x1 minus x2. If you get the x1 and x2 mixed up, it doesn't matter as long as you're consistent. So if we look at it, well, the y1 is going to be 0.75, y2 is 0.11. So that's 0.75 minus 0.11 divided by my difference in x values, which I'm going to have to flip the page over quickly, 0.47 minus 0.07. Okay, notice it's not a work of art, but it's just clear. You can read it. As long as you can read it, that's fine. So 0.75 minus 0.0, that's 0.64 divided by 0.4. Well, if I go off and I measure and I sort of calculate that, well, I have to get a calculator out for this one. I can't have a preset value in this one. I know what it should be. So it would be 0.64 divided by 0.4 is 1.6. 1.6, but it says giving appropriate units. This is where nearly everybody loses the extra mark. So if we give appropriate units, well, delta y we know is going to be d squared. We know that delta x is h. So d is a distance, it's distance squared, so it's meters squared divided by meters, which cancels with that, and you end up with meters. So it's 1.6 meters. Okay. Now the next part that's a warm up into the next part, which is all about dimensional analysis and units. You have to use base SI units to prove that that formula is dimensionally correct. What it means is it homogeneous? So d squared, d is a distance, so that's meters squared. So we've got 2. Well, 2 doesn't have any units, but v has got units of meters per second. Now it says show, so you've got to show the steps. If you skip steps, you lose marks. So it's meters per second all squared multiplied by h. H is a distance in meters, and g is an acceleration, meters per second squared. Yes, you could put newtons per kilogram, but it wouldn't be it would be kind of the long way round. So if I multiply that bit out, I end up with meters squared, seconds to the minus 2, because I square the meters and square the seconds to the minus 1, multiply it by meters, divide it by meters per second squared. The meters cancels with the meters there. The seconds squared cancel with the seconds squared there. And we end up with meters squared equals meters squared, and that's good enough. Okay. It then says hence use your value for the gradient of the graph. Well, in other words, using that formula. Okay, so this formula is probably correct. So what we've got here is we've got d squared equals 2v squared over g multiplied by h. Well, on the graph you put d squared on the y-axis and you put h on the x-axis, and you know if you get a y equals mx graph, you know that m is the gradient, so that value 2v squared over g must be equal to the gradient. So the gradient is equal to 2v squared over g, so g is equal to 2v squared over the gradient. So that's 2 times 4 squared over 1.6, which comes out to be 20 meters per second squared, which is twice what you'd normally expect for the acceleration due to gravity on Earth, but the question said nothing about it being on Earth, so all is forgiven really. So number 5, we've got a toy car. A toy car with a motor travels up a wooden board. The car is travelling up the board at a constant speed. It says you've got to put arrows to show the weight of the toy car, the perpendicular reaction force of the board on the car. Perpendicular, that means perpendicular to the wooden board. And the driving force of the car, F. So we know the reaction force is perpendicular. That's a no-brainer. So we call that R. Okay. The next one we show the vertical force, which is the weight due to gravity, mg. It tells you to label it mg. Okay, mass times gravity. That's the weight of the car. And we know the force on the car is going to be somewhere in that direction, and it's going to be going up the ramp because it's the driving force of the car. Okay. Now, it then says explain why the car is in equilibrium. The car's in equilibrium. Well, if you think about it, the net force must be equal to 0. Okay? The net force must be equal to 0. In other words, all the forces balance. All forces balance. So, there is no acceleration. And that's how you know that that it's in equilibrium. There's no acceleration, okay, because there's no net force, therefore the forces must be balanced. The car has a mass of 0.5 kilograms. The board is tilted at an angle of 30 degrees. At that angle, the car travels at a constant speed. So now we're getting some values in here. I want to calculate the force on the car due to the motor. So we're kind of ignoring friction a little bit here, but never mind. So we know it's 30 degrees. So we know the driving force of the car is somewhere in that direction. We know that the force due to gravity is in that direction. And we know that the perpendicular reaction force is in this direction here. Okay? And that is going to be a right angle. So that's the force we want to work out. That side of the triangle is mg. Now, if geometrically speaking, if that is 30 degrees, then so too must that be, if you think about it. Okay, the two angles have got to be the same. So we've got a 30 degree angle, a right angle triangle, a hypotenuse of mg, which is easier to calculate because we've got the mass of the car, we know what g is, we know it's 9.81. We want to work out f. So f is equal to mg times the sine of the angle theta. So that's going to be 0.5 times 9.81 times the sine of 30 degrees. Sine of 30 degrees is 0.5, by the way. So we end up with a driving force of 2.45 newtons. And there's your answer. It's that easy. But it's just a question of using a bit of geometry. Now, as we move on, as I'm sure you wish I would, the next part looks like an horrendous question, but actually it's easier than it looks. Got a force time graph caused by the car crashing into a wall. Well, that's not something I would advise doing, but there we go. You've got a data logger. That's a device that records data over time, over very short periods of time. It records the force on the wall due to the car crashing into it over time. The force time graph is shown in graph number 1. Here it is. That's the force measured. You want to calculate the maximum force on the car. First of all, it says state, which means you don't have to calculate. Well, if this is a force time graph, the maximum force is going to be the one at the top here. Well, we haven't got a very good scale on here, but I reckon that's 2/3 of the way between 600 and 700. So we might as well say that's 670 newtons. Perfectly acceptable to say 660. You might get away with 650, but that's pushing your luck a little bit. Okay? Try and be as precise as you can. You can sit there and measure it, because that is between that line and that line. You've got almost exactly 6 millimeters, and that sort of mark there goes exactly 2 millimeters down, so it's 2/6. In other words, 1/3 of the way from 700 to 600. So it'd be 667 or something like that. So 670 is absolutely fine, as is 660. Then it says use the graph to estimate the total change in momentum of the car during impact. So the bit of physics here is we know it's the area under the graph. So if we want to measure the force of the impact, we're looking at measuring the area of an odd shape. Now there are lots of ways of doing this. As long as you are applying correct physics, it's absolutely fine. Well, first of all, if you want to work out the area of one square, you know that's going to be 100 newtons multiplied by 50 milliseconds. So we could say one square, okay, rectangle, but it's good enough for me. One square is going to be 100 multiplied by 50 milliseconds. That's 0.05 seconds, which is going to be 5 newton seconds of impulse. We then count the number of squares underneath. Well, you've got 1, 2, can't quite count that one, it's less than half, can't quite count that one, it's less than half. So we start here, 3, 4, 5, 6, 7, alright, we can count that one, 8, that one's just about more than half, I'll call that 9. So we've got 9 squares implies 9 times 5, which is 45 newton seconds. Okay, if it's not exact, that's absolutely fine. You can do it by drawing a triangle if you really wanted to. You could try and work it out by sort of working on sort of average values and lines of best fit and the like. So you could do that sort of thing like that and like that. For example, you could measure that height there, and you could actually measure the area of that triangle if you really wanted to. Anything whereby you're measuring the area under the triangle, or the area under the graph, sorry, is absolutely fine. Okay, so don't sweat it. So if the mass of the car was 0.5 kilograms, it came to rest after the collision, estimate the initial speed of the car. So we know that the momentum, the impulse it's given, is mass times velocity. So its change in impulse is going to be the mass times the change in velocity. So if we want to work out the velocity of the car, we know it's the change in impulse divided by the mass. So the change in impulse is 45 divided by the mass, which is 0.5. We end up with 90 meters per second, which is a bit fast for a toy car, but it'll do nicely. Now we're on to quite a tricky question about moments and centre of gravity. Now the centre of gravity, remember, is the same thing as centre of mass, only replace the word mass with weight. So the centre of gravity is the point on an object, or the location on an object, at which all its, now you've got to be careful, it's centre of gravity, so it's got to be all its weight can be said to act. Okay, moment, now it's 1 mark, so it's force times perpendicular distance. That's all you've got to say. Don't say turning effect. So force times perpendicular distance, that'll do nicely. You could say force times perpendicular distance between the line of force and the pivot if you want. If it was a 2-mark question, that would actually get you the 2nd mark, but here it's a 1-mark question, so we just want the simple answer. So 2 conditions necessary. Well, and notice I've skipped the diagram for a minute. State 2 conditions necessary for the plank to be in equilibrium. So if the plank's in equilibrium, first of all, sum of all clockwise moments must equal sum of all anti-clockwise moments. Okay, it's as simple as that. For the other one, let's say the other condition, of course, is going to be the sum of all forces must equal 0, okay? Because in other words, all the total upwards force must equal the total downwards force. It's as simple as that. That's the bit that people miss out. They get that slightly, they forget about that bit. Now the next bit, if I give you the question, then we'll have to come back to the diagram. Got to determine the weight of the student. Now this is a bit of a nightmare. So we take this in steps. This is, when you actually take this in steps and you read the question carefully, you suddenly realise how easy this question is, even though it looks difficult. So you want to work out this value of W here. It tells you that there is a pivot, P. So where's the P? There's the P. So there is your pivot. If you've got a pivot there, suddenly you're just doing a basic balancing equation, a balancing question. So first of all, we have to work out what the distances are of all the forces from that pivot. So this is 0.5 and this is 0.3. This distance here is 0.2. If we want to work out this distance here, well, it's halfway along. It's uniform plank, so this will be halfway along at 1 meter. If this is 0.5 meters from the pivot, then this distance here has got to be also 0.5. Okay, and then you want to work out this distance here. Well, if that's going to be again 1 meter, 2 meters there, you know that's going to be well, it's 20 centimeters from the end. We know that's that distance from there to there is 1 meter, but we want to work it out from here. So we need to redraw this over down here. I think it doesn't fit up there. We don't really need that. So if we're trying to redraw that, we've got 0.5. Well, from there to there's 1 meter. There minus 0.2 is going to be 0.8. So 0.5 plus 0.8 is going to be 1.3 meters. Okay. Right. So the next thing to do is to then translate that into the question. So everything trying to turn this clockwise is this force and this force. They're both trying to turn it clockwise. Anything trying to turn it anti-clockwise is the weight of the student. So if we want to work it out, we know that clockwise moments equals anti-clockwise moments. Okay. We're actually going to swap them over. You'll see why in a minute, because the anti-clockwise moment is from the student, which is going to be the weight times 0.2. Weight times 0.2, which is going to be the total clockwise moment. So we've got the two forces. So we've got 80 times 0.5 plus 70 multiplied by 1.3. Okay, so if we've got that, then we can start to do some calculations. Well, the weight of therefore is going to be W, which is 80 times 0.5, which is 40 by the way, plus 70 times 1.3 divided by 0.2 is going to give you something in the region of 655 newtons, which is about 65 kilos or so. So the weight is going to be, well, let's keep it 655. You don't have to worry about significant figures. Okay, there it is. Easy as that. It's just an equation. So if you only got the 70, if only the 70 Newton weight is moved, then there's going to be a maximum weight the student can be the maximum weight of the student that can be determined using the arrangement. Well, there is a maximum. You have to state and explain one change that can be made to increase the maximum weight. So if you wanted to weigh a heavier student than was possible, what would you have to do? Well, there's lots of different things. You could have a heavier weight, you could have a longer plank, but the simplest way is just to move the pivot. which way? Well, I'd move it off to the left so you can get a greater moment and the student makes a smaller moment. Okay, so I would move the pivot left. Okay, so the student has a smaller moment, a smaller moment. Okay, that's the basic idea. That's how I do it. That'll do nicely. So then we got to multiple guess. So multiple guess is fairly simple. We've got the acceleration of free fall on a planet is 1/6 of what it is on Earth. So the mass of the body on the planet is 30 kilograms. So in other words, anything's going to weigh a sixth of what it weighs on Earth. So its weight on Earth is 30 times 9.81 divided by 6, because it'll be 1/6 of that. It's going to give you 49. Lovely, that's easy. Next one, it wants you to work out which set of results could be described as precise but not accurate. So precise means they're close together. Accurate means they're close to the real value. So if you took an average of all these results, that would be accurate. So it's not that one. If you took an average of these results, well, they'd be a bit high, but they're not terribly precise. That one's way out, so it's not precise. If you look at this one, well, again, they sort of waver all over the place. So again, it's not precise. These are very close together, but they're all significantly less than 9.81. So they're precise, but they're not accurate. So that's what we're looking for. And then number 9, we've got a body falling in a uniform gravitational field encounters air resistance. The air resistance increases until terminal velocity is reached. Which factor does not affect the terminal velocity? Well, the denser the air, then the lower the terminal velocity is going to be. Obviously, the more molecules to bump into. The height from which the body falls, well, the height does affect the density of the air itself, but only if you change it a lot. So actually, that's not going to have much of an effect on the terminal velocity unless it's a massive change in height. The mass of the body, well, we know the greater the mass, the greater its terminal velocity, because it has a greater weight and therefore it has to be overcome by the air resistance. The shape of the body, well, we know that if you're skydiving, you spread your arms and legs out, your terminal velocity decreases. So B is definitely the correct answer here. Okay, last 2 questions to go. It says which one of these is not Newton's laws of motion. Now these are all correct facts, but this top one that says a total momentum of a system into interacting bodies remains constant providing there's no external force. That's true, but it's not Newton's laws of motion. That's just the principle of conservation of momentum. The rate of change of momentum is directly proportional to the external force acting on the body. That's true. If a body A exerts a force on body B, then body B exerts an equal and opposite directed force on body A. That's the third law. That's true. That's Newton's laws. A body continues in a state of rest or of uniform motion in a straight line unless acted upon by some external force. That's the first law of motion. So A is definitely the one that's not in Newton's law. It then says what is meant by the weight of an object. Well, they could all be correct because the mass multiplied by acceleration should give you a force. Yeah. The mass of the object multiplied by gravity, well, it's not very well expressed, but yeah, that would give you the weight. The gravitational force, gravitational field, that's looking more like a definition, isn't it? And that's what we're looking for. So the gravitational field acting on the object might result in the weight, but the weight itself is the gravitational force on the object. So it's B is the answer. And that is how you answer the extra specimen exam paper. Okay, now I've taken you through this. I've taken you through some of the mistakes that candidates commonly make and made it as if I was making the mistake myself to give you a reminder of how important it is to check your work. So this would be a 1.5 hour paper. Now I've gone through it in 1 hour and I've been explaining it as we go along. It's very important when you do these papers that you realise you've got to spend the time allowed. Don't be tempted to leave the exam room early. What's really important, and what I would do if I was doing this paper for real right now, is I would actually go through question by question, redo all my calculations, check I've typed numbers correctly into my calculator, and check that I've actually expressed the answers to the best of my ability. Having said that, that is how you do the paper. Now you know that the papers are of a very, very similar style to all the specimens and the practices I give you. So you should pay particular attention to the techniques that are being used in each question. Although each question is different, the questions are different, the actual context changes, but what you're required to do remains fairly similar to keep the style of the paper nice and uniform, and therefore enable you to be able to access the questions more easily. I hope that's been useful to you. Do have a go through it again. Feel free to watch the video again and pause bits and pore over the question, particularly on parts where you didn't understand what I was saying. Okay.